Welcome to today's action-packed relativity lecture. Today we're going to do either 3 or 4 things. The first is time dilation, then the twin paradox, a treatment of the twin paradox. Paradox is in inverted commas because all of the paradoxes of special relativity are apparent paradoxes, which typically arise because of an implicit and ultimately illogical mixing of pre- and post-Einsteinian ideas. So we'll give a cursory treatment of the twin paradox. We'll give a full treatment of the twin paradox, by the way, in the tutorial, in the next tutorial, for which the notes have already been uploaded. How do you transform velocities? You know, with the Lorentz transformations, we were transforming what in many respects is the most basic thing in physics, a click, the x, y, z, t, the point in space-time, the event. But we fill the physical world with, that's just the stage, right? The x, y, z, t's. The Lorentz transformations tell you how to transform the stage, the coordinatization of space-time. But we want to fill this stage with particles, with fields. We need to learn how to transform not just events from frame to frame, this is the Lorentz transformation, but also all of our physical quantities with which we work, including velocities, including speeds, including gamma factors, and we do all of this in section 15. And this begins a hierarchy of objects that we transform from one non-privileged inertial frame to another. By the end of the course, you'll be able to transform many quantities from one non-privileged frame to another. Events, we can already do that. Positions, events, energies, momenta, velocities, accelerations, speeds, gamma factors, electromagnetic fields, and the list goes on. Lastly, if we have time, we'll do the so-called drag effect, which is also called the flying fish tank. So over to time dilation. The Lorentz transformations do not have an absolute time. That time, as I've emphasised previously, has a certain plasticity, well, it's not an absolute in relativity. And as a way of examining this, as a logical consequence of the Lorentz transformations, we take our usual pair of inertial reference frames, S and S prime, in standard configuration with respect to one another. S prime moves relative to S along the x equals x prime direction. And what we want to do is to attach a clock to the origin of S prime. So here we have our clock attached to the origin of S prime. That's meant to be a clock. And we want to ask the question, if this clock is ticking away, so it's going tick, 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 according to the, well, it's a clock that's rigidly attached to the origin of S prime. So if you were S's and I was S prime, I'd have my clock ticking, and I would say that that clock ticks every t0 seconds. So just to be concrete, let's have a tick and a tock, for the clock in the S prime frame. So according to the S primed frame, our tick and our tock are 2 events. Tick, tock is a pair of events. We could call them tick and tock. We could call them P prime and Q prime. And I'm putting primes because we're in the S prime frame in which the clock is at rest. And the tick I'm going to write as 0, 0. Now the first coordinate is going to be time. The second coordinate is going to be position, in fact x position. I could write down the y and the z variables, but they're just going to be doing nothing, so I'm going to leave them off, time and position. And so my tick is going to occur at the origin of S prime. This is time prime, right? Origin of S prime, the origin of space and the origin of time. That's my tick. My tock, by construction, by definition, by decree, will happen t0 seconds later. And I'm not priming this because this is what I would call a rest period. This is the period of the clock's ticks and tocks according to S prime. It is the period of this moving clock in a frame of reference in which it's at rest. We call that a proper quantity. So when we speak of the proper, the proper value of any quantity, we refer to the value that quantity takes in a frame in which the relevant object is at rest. So this is the proper period of the clock. So the clock has a proper period. Time's relative, so we can't speak of the period. We speak of the proper period as T0. We've already used the term proper before, proper length, for example. If I have a ruler, moving rulers have different lengths to stationary rulers, but the proper length is when you bring the thing to rest relative to you and you measure its length. That would be the proper length. The value the quantity has in a frame in which the object being measured is at rest. The proper period of the clock is T0, and we denote it as such. But we want to ask the question, what is the period of this flying clock? What is the period at which this clock ticks according to S prime? So we're going to need to transform. So we have S prime, we have our tick and our tock, P and Q respectively. Time first, X position second. Now I want to go from the primed to the unprimed frame. Now, the Lorentz transformations let you go from unprimed to primed. This is going to be an inverse Lorentz transformation, but remember, a V reversal, you can take any valid relativistic transformation and convert it to another valid relativistic transformation via a V reversal. That two-step process. Step 1, interchange primed and unprimed quantities. Step 2, replace V with minus V. You prove this as an exercise, and with this V reversal you can, on inspection, write down the inverse Lorentz transformations, or you can look them up in the relevant equation. However you do it, you can inverse Lorentz transform the tick and the tock. P prime and Q prime will become P and Q. By the way, because the Lorentz transformations are homogeneous and linear, it should be no surprise that 0, 0 inverse Lorentz transforms to 0, 0. But Q, on the other hand, Lorentz transforms, or inverse Lorentz transforms to the following. G is the, gamma is the usual relativistic gamma factor. V is the velocity of S prime relative to S. So what we observe, this is the period, what we observe is that the moving clock runs slow. The moving clock runs slow by a factor of gamma, that the moving clock runs slow by a factor of gamma. So instead of having a period of T0 according to S prime, the period is now gamma T0, which is the same thing as this. The moving clock runs slow. So this is very, very, very non-intuitive, and also a bit dissatisfying, because it sort of popped out of the algebra, but the physical meaning of what's going on is not particularly clear, and our intuitions leave us in the lurch, right? Because, as I've said several times already, we have terrible intuition for the fact that the speed of light is not infinite. There's another way to derive this result, which is less swift, but more conceptually satisfying. Now, because the mathematics is very trivial, I'm just going to sketch the essence of it. It's a thing called the Einstein clock. And so the Einstein clock is a special kind of clock. It's just a pair of mirrors. And here is an Einstein clock which is at rest relative to all of us. And we're approximately in an inertial frame. And all that happens is that light bounces up and light bounces down. And each tick is going to be when light strikes the bottom plate. So tick, 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 etc. So this is the Einstein clock. And if this is light going up and down, these are perfect parallel mirrors. Those mirrors are separated by a certain distance, which you could call L0, for example. Then you could work out the period at which this clock ticks via time equals distance over speed. So this is an Einstein clock stationary relative to you. But let's now have an Einstein clock stationary relative to you. The floor is the bottom mirror, my hand is the upper mirror, light's just bouncing up and down. Now let's have this Einstein clock move relative to you. I don't have enough hand-eye coordination, but the point is the light's going to be coming from the ground, up, striking the top plate, and then moving down to the ground again. As far as I'm concerned, the light is always travelling vertically upwards or vertically downwards relative to me, and light travels at the speed of light. And so according to the moving observer, the clock does nothing different. Light travels at the speed of light, it goes from bottom to top and down again. But you, if I was frame S prime in frame S, what you would see would be the light begins at the bottom, the clock moves to the right, and you'd see a light ray doing this. So one period of the clock, of the flying clock, of the clock that's moving relative to you, you'd say, well, light actually travelled a bigger distance. And you could, trigonometry, and you could work out the distance that this light travels. And you could work out the period of this moving clock, and you would conclude, this picture tells you, this flying Einstein clock tells you, that the flying Einstein clock moves slow. So the moving clock runs slow, and the ratio of the periods of these two clocks will actually be the ratio of the lengths of those two light paths. And when you work out the ratio of the lengths of the two light paths, you get precisely this result. Now that's worked out in detail in the notes, but I'd invite you to ignore them and have the pleasure of discovering this formula for yourself using nothing more than very, very elementary physics and a bit of trigonometry. But this contains the conceptual essence of why moving clocks run slow. Now the argument is, there's a leap by the way, this is a particular form of clock, a light clock which will run slow. The argument is that any clock, any moving clock will run slow. Ask yourself whether you believe that leap. But the point is, if the Einstein clock moves slow, the claim is that any such clock, or any clock will move slow, whether it's a nuclear clock, a nucleus waiting to decay, an unstable particle waiting to decay, an Einstein clock, a wristwatch, and also biological processes. All of these things are going to run slow, almost by demand. The point is, moving clocks run slow. It's a trivial algebraic consequence of the Lorentz transformations, but can also be thought of geometrically as follows. Again, I'll let you work through the algebra. That's all I wanted to say about time dilation, except to make the point that this is very, very real. So as one example, if you have some high energy astrophysical event, a supernova for example, and it pummels the upper atmosphere with very, very high energy particles, it then creates a cascade where that high energy particle bangs into some particle in the upper atmosphere, and all sorts of particles can be created, including a shower of muons. And muons are short-lived particles. If I have a muon here, on average it will live a certain amount of time. Let's call its average life, So it has a certain average life, which by the way is proportional to but not equal to its half-life. Let's talk about half-life for simplicity. This is a muon, it has a certain half-life. If I have a billion muons, on average they will live for their half-life. If I have a stream of muons, originated by these cosmic ray collisions in the upper atmosphere, then I have moving muons, and moving muons should run slow, their clocks should run slow, and if the moving clocks run slow by a factor of gamma, then the half-life should be multiplied by a factor of gamma. Short-lived particles that are short-lived, half-life is a relative quantity. The half-life of this muon, relative to you, is different to the half-life of this muon, relative to you, right? If this moving clock runs slow, and a radioactive decay is a clock, then muons that are moving relative to you, such as the muons that are passing through your body right now from the cosmos, they should have a longer half-life, and they do, and you can measure this, and it's consistent with this calculation. One further point, which might sound a bit trivial, but it's actually a profound one. It's one thing to rub pieces of chalk over bits of a blackboard and to derive results such as moving clocks run slow by a factor of gamma, but it's magical when you actually go out into the world outside, measure muon half-lives, and there's a link in the notes that you can look up to see this done, a very classic experiment. And then nature, the measurements actually accord with your scratchings that you do as a physicist. That's an amazing thing, at least in my humble opinion. Yes. Another good example of moving clocks running slow, by the way, is that you can do an experiment where you get two very, very high precision watches which are synchronized. You then put one into an aeroplane, fly it around the world a couple of times, come back and compare the watches, and they won't agree. I'm referring to a classic experiment by Hafele and Keating that was done centuries ago, or more precisely in 1971. and you can compare the clocks, and they won't agree. Again, the plasticity of time, and one of the contributing features to the fact that the clocks don't agree is this moving clocks run slow idea. There's another contributing factor, by the way, due to general relativity. Gravitational fields screw up clocks as well. That's another effect, which is a story for another day and another course. Moving clocks run slow, time is not absolute. But again, it's sort of infused into our bones, the implicit assumption of absolute time. I want to mention now the twin paradox. And I'm going to treat it in such a way which is as satisfactory and unsatisfactory as our first treatment of time dilation, in the sense that I'm going to give you a I'm going to state the twin paradox. I'm then going to briefly explain why it's not a paradox. But that explanation, in inverted commas, is going to dismiss the apparent paradox, but in a way that doesn't shine much conceptual light on the paradox, which should piss you off. And you should say, I want to understand the physics of what's going on, not these smart-ass arguments that can dismiss an apparent paradox, but I want to understand the physics more deeply. Just like, this is a smart aleck derivation of moving clocks running slow, which doesn't really emphasise the conceptual essence of what's going on. This latter calculation, while it might be less elegant, does bring forward the concepts much more clearly. What I'll do today, in today's class, is to have the smart-ass argument, dismissing the twin paradox, which is an apparent paradox. But we'll go through the twin paradox in full in the next tutorial. So the twin paradox is as follows. We have two twins, A and B. In fact, let me call them Jack and Jill. So we have Jack and Jill, who are twins. And Jack and Jill are both infinitely small, zero mass beings that were born at exactly the same instant of space-time in the inertial frame. Yeah, you get the idea. Jack and Jill are twins. Jill is an astronaut and Jack isn't. So what happens is that here's Jack and here's Jill, and let's assume that the XYZ T frame rigidly attached to the Earth is approximately inertial. And Jill, being an astronaut, is going to, they've got clocks, they synchronise them. In fact, those clocks are called their ages, which is the same. Jill then hops into her spaceship, very, very brief period of acceleration, after which she travels at constant velocity v for a long time, according to her. Then there's a very, very brief period of deceleration. But these are brief periods, so who cares? She turns around and comes back with equal but opposite velocity minus v, slows down, decelerates, and now she compares her age with Jack's. And the statement is, if moving clocks run slow by a factor of gamma, never mind these extremely brief periods of acceleration, the rate at which she ages on these two journeys is gamma times slower, and here v is the magnitude of v. The rate at which she ages during her journey is gamma times slower than the rate at which Jack ages. Therefore, Jill comes back younger than Jack. Fair enough, time's relative, that's it. Get over it, your intuition's wrong. Jill comes back younger than Jack. The apparent paradox is to say, well, I know about the relativity principle, and I could view this whole experiment from a frame of reference that is rigidly attached to Jill. And Jill would say, so here's the frame of reference attached to Jill, so she's going to be at rest for the entire duration. I'm just going to have Jill's XYZ T, and let's look at everything from the perspective of that frame. From this perspective, Jack and the entire planet Earth accelerate, right? Same picture, or pretty much the same picture. ... Therefore, Jill comes, Jack, moving clocks run slow. Jack's clock ticks slow relative to Jill's. If you've got A and B, A says that B's clock moves slow. B is moving relative to A with a velocity v. But there is no absolute frame of reference. So A says that B's clock runs slow, but the relativity principle says that precisely the same scenario is this. There's no absolute frame of rest. Let's choose B as it being at rest. B says that A's clock runs slow. So A says that B's clock runs slow, and B says that A's clock runs slow. That's a logical contradiction. Therefore, relativity is wrong. Applied to the twin paradox, the second picture would lead one to conclude, by symmetry, by the relativity principle, one would conclude Jack comes back younger than Jill. This gives the opposite conclusion. Jack comes back, here Jill comes back younger than Jack, and here the opposite is true. Therefore you have the so-called twin paradox. Now the unsatisfactory resolution of this paradox for the purposes of today's class is just to point out that this diagram hides a certain fundamental dissymmetry between Jack's experience and Jill's experience. And here's the point. Jack spent the entire duration of the experiment, let's call this the experiment from the instant at which Jill's ship takes off through to the instant at which Jill's ship comes to rest at the end of her journey and the watches are compared. For the entire duration of this experiment, Jack stayed in one inertial reference frame. Jill, on the other hand, was in a sequence of inertial reference frames. Number one, the approximately inertial reference frame attached to the Earth. Then she accelerated to a second inertial frame, which she was in for the vast majority of her forward journey. Then she accelerated to a third reference frame, coming back, and then she decelerated to a fourth inertial reference frame. Jill was in 4 separate inertial reference frames, connected by periods of acceleration. Jack, on the other hand, was in 1 such inertial frame. Therefore, the putative symmetry claimed by this misleading diagram does not exist, and hence these 2 situations should not necessarily give the same results. Therefore, just because I say that Jack is older than Jill, that does not imply the opposite, which makes the point that the paradox doesn't exist, because the assumed symmetry that this diagram is misleadingly pushing you towards doesn't exist. But that doesn't change the fact that when you have 2 observers moving relative to each other, A says at uniform speed, A says that B's clock runs slow and B says that A's clock runs slow. What's going on there? That's really the path or the question that you want to punch through and examine in properly and satisfyingly understanding the twin paradox. And that's what we'll do in full detail for an entire tutorial class. If you want to look ahead, the notes are already uploaded on Moodle. So on that slightly unsatisfying note, I'm going to put the twin paradox to one side and move on to section 15, which is the velocity transformations. And in fact, in this section, we won't just be able to transform velocities, but also speeds and gamma factors, although I will leave several things as exercises. So again, I want to make the point that we have our 2 inertial reference frames in standard configuration. It's times like this you wish you had PowerPoint, you could just press the button and there it would be. And we know how to transform the most basic object, the event, the XYZT, yep. But we want to be able to transform more complicated objects. Ultimately, energies, momenta, particles, energy, momenta, electric fields, magnetic fields, etc. Directions, the list goes on. Colours, frequencies, we'll do them all. Accelerations. But for now, we want to be able to transform velocities. And a starting point is going to be the differential form of the Lorentz transformation. So I'll just remind you that the Lorentz transformations, the forward Lorentz transformations with the usual standard configuration are as follows. The usual gamma factor, x minus vt. For the second one, t minus vx on c squared. Notice the judicious gaps I'm leaving, y and z. Because these things are linear and homogeneous, they have no additive constants and they're linear, infinitesimal coordinate differences will transform in exactly the same way. So here is a differential form of Lorentz transformations. Why am I talking about differential forms? Well, what is velocity? You know, if I have a piece of chalk moving through space and we ask, what does velocity mean? Well, if I place the chalk with my hand, it's, you know, a trajectory is nothing more than a sequence of events in space-time. Just to repeat, a trajectory, and this is a trajectory in space and time, is nothing more than a sequence of events. And the essence of velocity, of motion, is to consider not one event, but a pair of events. And if this is a trajectory in space-time, it's a continuous curve not in space, but in space-time, then I'm going to be wanting to look at what is the velocity at a given event. I'm going to be intrinsically concerned with pairs of events, because that's the essence of motion, moving from one space-time point to another. These are going to help me. How are they going to help me? Well, let's have some definitions. So I have my pair of inertial frames, and I'm going to have some, this is not an event now, this is a point moving, yep. And that moving point particle is going to have some velocity according to S and S prime. And the velocity of that particle will be called U according to S, and will be called U prime according to S prime. And we want to ask the question, how do you transform U prime to U, and conversely? These will be the velocity transformation formulae. Notice that there's two velocities here. There's the velocity of the particle, which, again, the particle is a geometric object which exists independently of how you choose to coordinatize space-time. But I would call it the velocities in S and S prime respectively, U and U prime. But we have a second velocity. In fact, there's three velocities here, U, U prime, and V. So we need to be careful of that. According to S, the velocity is U, and its Cartesian components in three spatial dimensions I'll call U1, U2, and U3. Now, according to S, X, Y, and Z will be the coordinates of the particle as a function of the time relative to S. So X, Y, and Z here are functions of the time t according to the inertial frame S, similarly for S prime. So when I write down dx dt, dy dt, etc., I'm considering X, Y, and Z to be functions of the time t according to inertial frame S. Similarly for S prime, that velocities, U prime has these Cartesian components, which are going to be dx prime dt prime, etc. Again, notice that both the coordinates and the times are changing. And this is where our differential form of the Lorentz transformations are going to help us. Yep. So I want to write down U prime, U1, U2, U3, dx dt, dy dt, dz dt. So I now want to use these instead of dx, dy, dz dt. I want to make use of these quantities here. I've done one thing wrong, which is I need primes here, because I've chosen U prime. I could have chosen the other one. I just would have needed the inverse versions of these. So instead of dx prime, I'm going to write d gamma. D gamma, shit. There's no d here. I'm going to write gamma into dx minus v dt. Instead of dy prime, I'm going to write dy. And instead of dz prime, I'm going to write dz. The bottom, well, I have dt prime, and dt prime is this thing here. So gamma, etc. dt minus v dx on c squared. And then I repeat this. So this is already looking a bit messier than you might expect. Yep. So there it is. Now I can cancel these gammas, which is good. The next thing that I want to do is to divide numerator and denominator by dt. So I'm just going to write over the top of this equation. In fact, no, I'm not. I want to divide numerator and denominator by dt. So this becomes dx dt. So dividing numerator, every term in the numerator and denominator by dt. This will become dx dt, which is the same thing as u1. Divided by dt, that becomes dx dt, which is u1. I've divided through by dt, so the dt disappears. I've divided through by dt, so this becomes dy dt, which is u2. And similarly for u3. Down the bottom, I've divided through by dt, so this becomes a 1. This becomes dx dt, which is u1. Gamma factor, divided by dt, which gives a 1. V on c squared, dx dt, which is u1. Same denominator here. So this is our formula for transforming our velocities. These are the Cartesian components of u prime, u1 prime, u2 prime, u3 prime. So that's it. We have our velocity transformation formulae. Yep. This thing, I won't write it out explicitly, equals u1 prime. This thing equals u2 prime. And this thing equals u3 prime. So these are equations 77. That's good. Again, those formulas look more complicated than you might expect. But that's life. This is relativity. Those are the velocity transformation formulas. And that will let you go from one way to the other. In this case, from unprimed to primed. But as always, we have a formula, these transformation formulae, these velocity transformation formulae. The first of which, for example, is u1 prime equals u1 minus v, etc. Again, u1 and u1 prime are respectively the x and x prime components of the velocity in s and s prime. V, on the other hand, is the velocity over which the two x/x prime axes are sliding relative to one another. And I could write down the formula for u2 prime and u3 prime. I won't. But what I want to do now is to apply that v reversal that I mentioned earlier, the v reversal, in order to turn one valid relativistic transformation into another. It's a two-step process. I replace primed with unprimed quantities. So where there's a prime, I get rid of it. Where there's no prime, I put one there. So v is not primed. Yep. And I replace v with minus v. So if we focus on this formula here, I've just inverted the first velocity transformation formula using a v reversal. This formula has a name. It's called the Einstein velocity addition formula, because what we're doing here is adding collinear velocities. If you were to formally take the speed of light to infinity, or more precisely have v much less than c, and your u1 primes, etc., being very subluminal, this would disappear, and you would have the normal velocity addition formula. Yep. If you're on a conveyor belt moving at speed v to the right, and you throw a tennis ball while you're standing on the conveyor belt with a velocity of u1 prime relative to the conveyor belt, then relative to the ground, you just add the velocities. That's the Galilean velocity addition formula, which, for example, says that if you shine a light beam on your conveyor belt, its speed relative to the ground would be c plus v, which violates one of Einstein's axioms. This is the Einstein velocity addition formula, which modifies the Galilean addition formula, but reduces to the Galilean addition formula in the appropriate limit. Einstein velocity addition formula. And this, by the way, you can keep adding velocities and it'll never punch through the velocity of light, and you can show that explicitly. So here's our Einstein velocity addition formula. So we've now learned, we're moving from describing the stage of space-time, transforming events from frame to frame, and now we're beginning to transform physical quantities that occur, or physical quantities associated with physical systems that live out their life on the stage of space-time. Now that we know how to, we can transform events, we know how to transform velocities now. We also know how to transform the speed of light. You don't, right? This is an invariant. The squared interval is another invariant, a thing that doesn't transform. The point is we ultimately want to build a hierarchy of quantities that describe the physical world and for which the transformation formulae are known. We're also going to demand that in order for a physical law to be correct, a necessary condition is that it will have the same form in different frames. Notice the abstraction. We begin with transforming events. Then I talk about transforming quantities associated with the physical world, momenta, energies, positions, electric fields, magnetic fields, colours, frequencies, times, lengths, ... But then we can transform something even more abstract. You can transform the laws of nature. You can transform the Maxwell equations from frame to frame. You can transform the Schrödinger equation from frame to frame. You can transform Newton's equations from frame to frame. And the demand is, if there's no privileged frame of reference, the only laws of physics I'm going to keep, I'm going to allow, are those whose form does not change with Lorentz transformation. Any law of physics that changes from frame to frame is out the door, right? Because that's in violation of the relativity principle. But I'm getting ahead of myself. We want to transform a sequence of quantities. We've just transformed velocities. Our next logical thing to transform is speeds. So the speed of our particle, by Pythagoras' theorem, is going to be adding in quadrature the three Cartesian components of the velocity. And we can also have the speed, u prime according to s prime, defined similarly, u1 prime squared, etc. And the question is, how do speeds transform? And I'm going to begin with the Lorentz invariance of the squared interval. We know that this squared interval is an absolute. Again, this squared interval is associated with a pair of events. And we learned in a previous class that this quantity delta s squared, the infinitesimal form of which is ds squared, so we're going to have two events. Again, this is really intrinsic to the motion of particles. It could, for example, a pair of events associated with a trajectory in space-time. Let them be infinitesimally close together. And so the vector in space-time that points from these one event to another infinitesimally close event. By the way, we don't have a notion of distance yet. We will get there, but this distance is going to be arbitrarily close. If this x-coordinate is x, I want this to be x plus dx, y plus dy, etc. This squared interval, we have a pair of events, and I'm going to describe the difference between these events, the infinitesimal difference as dt, dx, dy, dz, according to s, and the corresponding primed quantities according to s prime. And as a starting point for transforming speeds, I'm going to say that the squared interval, the primed coordinate would say that this is the squared interval. And the unprimed system would say that so the C is not primed. The unprimed, but the T is. The unprimed system would say that this is a squared interval. And the different inertial observers would disagree. They'd say, I say dt, you say dt prime. I say dx, you say dx prime, etc. But they would agree on this invariant squared interval because this thing is an absolute. It's unchanged under Lorentz transformations. It's a Lorentz invariant. So this is actually our starting point that's going to allow us to construct speeds. Again, we often speak about the process by which you discover these objects. You know, if you're a physicist working this stuff out for the first time, the logic will be something like, I want to transform speeds. I forgot this power. They have u1 squared, u2 squared, u3 squared. I'm really wrapped with this trick I had before of dividing through by dt. You know, when I divide through by dt, dx becomes dx dt, which is a velocity. Same story here. I'm going to ultimately want to divide through by dt squared. But where do I start? Well, I've got a sum of squares of velocity. That looks a little bit like the invariant squared interval. Let's write that down and see what happens. Let's stare at it and see if we can somehow mush these things together to get a transformation law for speeds. That's a kind of, I wouldn't call it e-logic, but it's sort of hunch-driven logic which is in no way linear, but rather just looks at the mush of equations that are relevant, stares at them and asks what connections can be drawn. This process cannot be systematized, but this is also where physics gets particularly interesting. Anyway, we have our invariant infinitesimal, our Lorentz invariant infinitesimal squared interval. And you can proceed in many ways. But what I'm going to do here is I'm going to factor out a dt prime squared from the left side of the equation, which is going to leave c squared minus dx prime squared over dt prime squared. Now what I've just done is mathematically abominable. Remember that this is going to be small but not infinitesimally small. It's not going to be so small that I get a derivative yet. I can take the limit as appropriate. The point is I'm going to replace dx prime squared divided by dt prime squared with dx prime all squared over dt prime squared. Take the limit. This will then become a derivative. Similarly for the other terms, dy prime dt squared, etc. So dt prime squared, etc. And already the physicist is happy because they're seeing a negative speed squared appearing here. And they're on a roll, so they're going to factor out a dt squared from the right-hand side. And they'll get c squared. Let's save ourselves some chalk. This is the negative of the speed prime squared. Yep. So this right-hand side is going to be the negative of the speed squared. So we've already got a formula that dt prime squared into c squared minus u squared equals dt squared into c squared minus u squared. And the second one, so the first one needs to be primed. So this is good. This is equation 82 in the notes. Now I stare at that and I don't know how to push it further, because this dt prime squared and dt squared is screwing me up a bit. So what I do is I go back to equation 60, which was one of the differential forms of the Lorentz transformation. The equation that has dt prime equals ... Because it's got a dt prime on the left and a dt on the right, and this dt prime squared and dt squared is annoying me. I want to get rid of it. I want something that relates to two quantities. Maybe the formula for dt prime is going to help me. dt prime equals, and since it's going to be squared, let me just go ahead and square it, and you'll get gamma becoming gamma squared. Let me be explicit, this depends on the boost velocity v, and then you'll have dt minus v dx on c squared. So this is just the squared version of the differential form of the Lorentz transformation, dt prime equals. So I have this. Now I'm liking this trick of multiplying or dividing by dt squared, so I'm going to factor out a dt squared from this. That makes me happy because I can turn a dt prime squared into a dt squared. And what I'm trying to do in going through this logic is not so much going through the steps, because it's just fairly basic linear algebra. What I'm doing here is trying to motivate the kind of thinking that goes behind seeing what steps to make. Then we've factored out a dt squared, so this becomes a 1 minus v on c squared, and this is going to become dx dt squared. And dx dt is nothing more than u1. So this is letting me turn a dt prime squared into something proportional to dt squared. And if it's proportional to dt squared, the dt squareds are going to cancel. Yep. So if you substitute this expression here, let me call it alpha, into beta, and then you do some more steps, which I'm going to leave to you, you'll get the following formula for how speeds transform. So c squared is the speed of light squared, u prime squared is the speed of the particle according to the primed frame. And then we get a surprisingly complicated formula. We were complaining about the complexity of these things. This is even more complicated. You might want to look at this formula and make sure that it's dimensionally correct. We have u prime squared, we have u squared, we have velocity. Now, I look at that formula and I don't like it. It's correct, and this is how speeds transform. But you know, the concept of a speed is, if you've got two frames which are boosted relative to one another in this direction, but you're talking about speeds in some arbitrary direction, you're going to have some non-isotropy, in the sense that this is actually a direction preferential formula, that there is dependence on the x or x prime component of the velocity. Oh, sorry, the x prime, the unprimed component of the x component of the velocity of the particle, or the projection of the s velocity on the boost velocity has a privileged place. It's also an ugly formula. I just don't like it. What this actually tells you is that speed is in some sense an unnatural quantity with which to work. These kinds of formulas are used occasionally, but rarely. This formula here, on the other hand, is much cleaner. What I'm trying to get at in a very roundabout way is that velocity can be bolted into a tensor. Tensors are going to be objects that the natural description of relativity is going to be tensorial. We're going to have a natural way of shoving velocities into tensors, and tensors are the objects out of which you build equations that have the same form in all frames, or for our course in all inertial frames. It's easy to tensorialize velocity. Speeds, on the other hand, do not naturally tensorialize. And when I say that this formula is distasteful relative to this one, this is actually what I'm getting at. Now, we're getting ahead of ourselves. We won't tensorialize our laws of physics until later. But again, I just want to end on that very profound point, which is the laws of physics are the same in all inertial reference frames. That is the ultimate and most condensed embodiment of the relativity principle. That is the ultimate and most condensed lesson to be learned from the null result of the Michelson-Morley experiment. But it also has a challenge that only physical laws that have the property of being the same in form in all frames are going to be valid. And also, we're going to have to construct quantities which we call tensors, which have certain transformation properties between frames, which reflect the fact that these are geometric objects which exist independently of how we choose to coordinatize space-time. And on that note, I'll stop. Thank you.